So in the last session, we introduced the notions of convection and diffusion, and we introduced the mass transfer flux. So the flux was estimated both in terms of convection and diffusion, and we showed that we could add the two together. And of course, we showed that the convection flux could largely be written as U times Ca. So in terms of the convection flux, there isn't much difficulty that we would have in estimating such a number. So the convection flux being U times C is fairly well defined. The linear velocity and the concentration, there's no real doubt about how we can estimate these numbers. On the other hand, in terms of diffusion, we can see that we have, number one, a gradient in concentration, and we'll show just now that's fairly easy to estimate. But on the other hand, we have this unspecified diffusivity. So this constant was introduced simply to grant us equality here. So we would like to write a quantity which is the mass flux here, and we know that it's proportional to minus the concentration gradient. However, to convert it into a simple proportionality, to convert a proportionality into an equality, we need to have the right coefficient here. So we need to know what multiplier to use for us to estimate this diffusion flux. And that's largely our focus in this session. So let's just expand on what we mean here first. So if we go back to the type of picture we were describing last time, if you have some tube, for instance, and if you happen to inject some of component A into that tube, so the red dots are component A, and let's say that tube was initially filled with evenly dispersed B. So you inject A into a specific location, so you have initially a high concentration of A there, and then that immediately means you will have a sharp concentration gradient. So you have a high concentration here and a low concentration there. That means there's a high driving force for A to diffuse away from that point of injection. So A will diffuse away, and so there will be some non-zero flux of A away from that point of injection. And number one, we can easily think of estimating a concentration gradient. It's as simple as specifying 2 points. Let's say we pick these 2 points. Then we could easily find a concentration here. Well, maybe not so easily, but at least in concept, we can understand that we can define a concentration in one place and a concentration of A in another place. And then the difference between these two divided by the width of that distribution, so call that delta. So that would be an approximate gradient for us. So, or minus gradient, right? Because we are looking at a lower x value. If we take x in this direction, if we take x as positive in this direction, then this is minus dc dt. It's an approximation to minus dca dx. So the point of mentioning this is just to say that it's fairly easy to understand how we can estimate such a number. It's simply the gradient of concentration. So this part is fairly clear to us. Now, what we also want is the flux here. So this is the quantity that we are trying to estimate. So we would like to know how fast is that fluid going, or component A, how fast is that fluxing in this direction. And of course, the flux is another well-defined quantity. It's simply the moles of A, the rate of A moving in this direction, the rate of movement of A in this direction, divided by the cross-sectional area here. So the flux is also well-defined. So the flux, we can say, is proportional to this gradient. But now let's think about the number that relates these two things, right? An actual flux here, when compared with the gradient here, is going to depend on a number of different factors. Number one, it may have something to do with the electrostatics of the molecules here. So for example, if you have atomic centers or molecules here which are highly charged. So let's say these molecules have a large number of electrons buzzing around them, then in effect there might be a strong force of repulsion in these molecules away from each other. And if you compare that with molecules which are smaller and have fewer electrons in their orbitals, we can easily imagine that they won't flux as fast away. So even if we have the same concentration gradient in two different situations, if we consider two different components A, so if we define A in two different ways, if we use two different chemicals for A in the same tube, you will get one mass flux for one of those chemicals which won't be the same as the other, and that will have to do with the nature of the molecule there. So the properties of the molecule and of its surroundings are going to govern the coefficient here. So we've defined conveniently dAB to this to be this coefficient, which tells us the diffusion rate. But this quantity depends on the very fundamental aspects of the molecules themselves. So we anticipate that we have to go all the way back to our fundamental physics if we want to really predict dAB. Well, all that work has been done for us. There has been a great deal of research into this and a great deal of work done on estimating the diffusivity. And in fact, it's not complete because we are still developing new correlations for new situations. So quite often what we do is classify the types of molecules involved. So for example, highly polar molecules will have one expression, and non-polar will have a different expression. Then for gases and liquids, there are different expressions because in the gas phase, of course, the molecules have far greater intermolecular spaces, and so the nature of the forces influencing the tendency of the molecules to push off is going to differ. So we anticipate that there won't be one unifying model, at least not at the outset, that will describe the diffusivity. But at the same time, the diffusion rate is important enough to us as chemical engineers that we have to become aware of some of the correlations out there for estimating the diffusivity. So in the session, we are not going to try to unpack the physics, the physics of the reasoning behind some of the expressions we'll see. It's simply going to be a high-level tour of some of the relationships that are available to us. Some other housekeeping things. We know, of course, that the molar flux has units of moles per meter squared per second. And then clearly our concentration, so that's the units here, and then the units of dCA dt. So Ca is moles per cubic meter, and then we are dividing by another space coordinate, so it's going to be moles per cubic meter per meter, so it's moles meter to the minus 4. So those are the units of dCA dZ. And so if those are the units there and these are the units here, then the units of dAB will be meters squared per second. So in SI units, those are the units of dAB. And so if you operate in those units, the typical order of magnitude for a liquid is 10 to the minus 10 to 10 to the minus 9, and then 10 to the minus 6 and 10 to the minus 5 for gases. So of course for gases are far more motile than liquids, so gases are freer to move around. That's why their diffusivities will be higher by orders of magnitude. But anyway, those are the orders of magnitude for those, so just check when you are using a value whether it makes sense. So anyway, that's just a bit of the background, and now let's look at some of the correlations. And so from this textbook, we are looking here first for diffusivity in low density gas mixtures, and as we said, we expect those to be functions of the molecular properties. And if you follow the references here, you can see how they come up with the expressions that follow. So the first step is to estimate this dA star, and then we estimate what's called the mean free path. So this is a number which indicates how the species are distributed across the space. So this is a function of the energy in the space, which is typified by the temperature and pressure and so on. Whereas the sigma refers more to the properties of the molecules. So these various quantities can be estimated through either the operating properties of the system, namely things like the temperature and pressure, or through the properties of the chemicals involved. So things like the molecular mass and so on, the mean free path and other estimates. So quite often there are multiple groups of constants that need to be estimated. So there's a lot of tabulation involved. So it involves looking up properties of species. And I'm just looking for an example here. So sometimes you can estimate some of these numbers through some correlations, and sometimes you have to look them up in tables. So if you look up sometimes the molecule, you can pick up, of course, from a molecule, we can, from the molecular structure, we can estimate from the atomic centers, we can extract some features or some quantities, and then some other quantities are tabulated for the whole molecule. So by looking up the right quantities in the available tables, we can use the correlations and so estimate our diffusivity. So in this first case, we were looking at the gas mass diffusivity. And so this is the eventual correlation. And you can see here, there are some constants like the Boltzmann constant and so on, molecular mass, as we said, operating constants as well, like pressure and temperature and so on. So it's a matter of using the right correlation. So it all begins with understanding what type of system we have. So if we know it's a gas phase system and it has a relatively low density, and those are typically precisely defined. So we set some criterion like the density is less than 1 kilogram per cubic meter and things like that. Then we know that this correlation applies. So it's a matter, if you like, of following the sequence simply, of identifying the type of mixture that we have, then using the right, looking up the appropriate correlation for that, and then assembling for ourselves the various properties of the chemicals involved, and then also knowing the operating parameters of the system. And then we just use the correlation and estimate the diffusivity. So that's what's available to us now, and we don't have to go through the painful process of trying to measure the diffusivity. So of course that's always an option to us. We can always construct an experiment like this where we apply some concentration difference and then measure the change in concentration over time, and then back estimate what the molar flux must have been, and so fit a diffusivity through it. So that's how these things are done. We the available researchers have estimated the molar flux through things like the concentration gradients, and then we can get as a ratio the diffusivity, and then over time it was shown that the diffusivity in this situation has this form, and so on. So that's one example, and in the notes there's more of a description about how to use these correlations. So we are not going to, we don't have to describe any of this in further detail. We just have to know how to use them in chemical engineering so that we can get these constants. This is also pretty important. So it's sometimes the case that we've done a lot of work to estimate a diffusivity, but of course that will be at a specific temperature and pressure, And instead of doing all the work of estimating the diffusivity at slightly different conditions, we can instead look at the correlation itself and figure out what the relationship with temperature and pressure was. So for example, here you can see the temperature relationship was T to the 3 over 2 and then 1 over P. And so you could simply correct for differences in pressure and temperature in this way. So you divide by T to the 3 over 2 and multiply by the new temperature raised to the power 3 over 2, and then the corresponding difference in pressure. And so you can simply correct for those. And here you do have to be careful that if there are some other quantities involved in that relationship, which are functions of your operating parameters, then you do have to correct these as well. And then that's a faster way of estimating a new diffusivity. Okay, so there are lots of worked examples, and you can get used to some of the available correlations in this way. So those are some of the correlations for the gases. And here's another useful thing that we can do, which is that the descriptions so far have been for binary mixtures. So in all these cases, our estimates of the diffusivity have been between two specific chemicals. So between chemicals A and B, we have a correlation developed. Now, obviously, most of our systems are not simple binary mixtures. You can have any number of species in your mixture. And then we could ask, well, then doesn't it depend on the relative concentrations among the species, and doesn't mole fraction play a role? So we may have any number of species here, and we have to still be able to estimate the diffusivity through the system. So here is a so-called mixing rule. So this pattern is fairly reliable in the case of gases. So it gives errors less than 15%. So we consider that to be a fairly low area in this context. So here, if you have, let's say you have n components in your mixture, and then if you wanted to estimate the diffusivity of component 1 in that mixture, then you use an expression like this, and these Y2 dashes are related to the mole fractions. So of course, if we have a mixture of n species, then we have n mole fractions. So the mole fraction is of course Y. And here we can see we need to use all the other components. So if we want to know the diffusivity of component 1 in the mixture, then we have to use Y dash and D, and this D is the diffusivity, the binary diffusivities. So it's the diffusivity of 1 in 2, and then the diffusivity of 1 in 3. So these are the hypothetical cases. So if you had component 1 and component 3, and if only those components were mixed together, then there will exist some diffusivity between 1 and 3, some diffusion flux of 1 through 3, and then that's the diffusivity. So assuming that we use all the correlations described so far to estimate those diffusivities. So we take all these binary diffusivities as given, and then we estimate these Y dashes. So Y dash is the mole fraction, so Y dash I is the mole fraction of component I divided by the mole fraction of all components, excepting the mole fraction of the sum of all components, excepting the component of interest. So remember, we are doing all this for some component 1. So we exclude all of component 1 here. So if it's the sum of all those mole fractions, then simply 1 minus the mole fraction of component 1 will be all the other mole fractions, the sum of all the other mole fractions. So yi dashed is yi over 1 minus y1. So we compute all the y dash values, and then we use that with the binary diffusivities in this way, and then we get the mixture diffusivity. And as we noted, this gave fairly good estimates of the mixture diffusivity. Right, so that's how we can estimate diffusivity for the gas, and then the diffusivity of a mixture of components in a gas. That all applied there. And then for liquid phase, there are other correlations available. So the Stokes-Einstein equation gave some good estimates in certain situations. So here, this is the Boltzmann constant. So this kappa is simply a defined number, and then there's your temperature, 6 pi r, where r is the solute particle radius. So that's again a property of the molecule, right? It's in fact a little crazy to talk about a particle radius when you're talking about an atom, but anyway, we have tables available of these quantities. And then your solute viscosity, so that's simply the viscosity of your solute. So this is one of the easier correlations to work with, as you can see. And then there have been attempts to generalize this by introducing this other function of the molecular volume. So of course, again, molecular volume is a property of your component, right? So the diffusing solute, and some of the forms are shown here. So you have this Wilkie-Chang expression and other expressions available. So again, you just look up for your system. What type of system is it? Are these polar liquids, or are these very dilute liquids, and so on? And so for your specific situation, there is very likely an appropriate correlation that you can use. And then you just have to look up what needs to be calculated and what properties of the species need to be looked up, and you can go ahead and use that correlation. Okay, and please work through some of these examples. It's always useful to develop some confidence that you can estimate at least the binary diffusion, the binary diffusion coefficients, and then you've got the mixing rule that can be applied on top of that. So that's how we estimate diffusivity. Now, that's the case if you have an infinitely large space and you are only concerned about molecule-on-molecule interaction. Now, in some parts of chemical engineering, we have close restrictions on the space that the molecules can move through. And maybe to unpack that a bit further, if you consider a reactor on the order of a cubic meter, right, with respect to a molecule in that reactor, that's actually a really tiny, with respect to the molecule, which is on the scale of angstroms. Remember, angstroms are on the order of 10 to the minus 10. So if you like, the width here is on the order of 10 to the minus 10 meters. So that is 10 to the minus 10 meters. And then, of course, the vessel itself is on the order of meters. So that is on the order of meters. So this is an incredibly large distance. This molecule, in effect, is just in a sea of molecules. The probability of striking the walls of the vessel are actually quite low in a given instant for a given molecule. However, in chemical engineering, quite often we are catalyzing our reactions. So we introduce little particles, and we rely on the molecule interacting with the particle to improve the reaction rate. And now, quite often in particles, we don't actually rely on reaction on the outer surface of the particle. We introduce tiny pores in these particles, because that really increases our exposure of what's in the particle. So if in the particle we have some transition metal which is going to do the actual catalysis, then we want a very high exposure to all that metal in that particle. So we actually want, if you were to zoom in on a particle, right, let's expand this particle. So if you have a particle like this, and you've got these nice metal centers embedded in the particle, so all these dots are the nice transition metal centers. Well, it's pointless to have a whole particle of transition metal centers and then rely on the reaction only happening out here on the surface. So instead, what you want to do is introduce pores through this particle. Sometimes these pores are actually the result of applying stress and causing little cracks to form. So you have very small cracks in these particles that form. And in fact, sometimes these cracks are so tiny that they are on the same scale as your molecule. So if you were to zoom in on one of these pores, right, so let's say we zoom in on this pore, right, your pore might look like this, and now you see your pore is actually on the same scale as your molecules. So if that's the case, then you will have collision with the walls of this pore. And so this then starts to rival the interaction of molecules and on molecules. So if this was a binary mixture of A and B, so let's say I'm drawing component B now. So we would like to estimate the diffusivity of A in B. But now we can see that A is also going to be knocking around against the walls of this pore as well. Then in this situation, we can no longer rely on the pure phase, the pure binary phase estimates of diffusivity. Now there's an additional interaction, which is collision with the walls, which is going to influence our tendency of molecules to move around. So if that's the case, we have to factor in this kind of interaction. And this was well studied by the researcher Knudsen, and we have the corrections that we are going to describe now. So this is what we've just mentioned. We have a pore, and we've got a particle that's knocking about against the walls of the pore. And then we have, of course, our binary diffusivity, which we can estimate. So this is what we can do from the earlier correlations. And then we also have to think of A sort of diffusing against the pore itself. And we can estimate a number for that diffusivity. So the Knudsen diffusivity of component A in these pores, that of course is going to be a function of the way this pore is constructed. So what's the diameter of the pore, for one? So the diameter of the pore features in there. This is Avogadro's number. This is the Boltzmann constant. The molar mass of A is here, and the temperature here. So in fact, everything eventually is rather well defined. So in some expressions of the Knudsen diffusivity, it's not the case that you have to look up too many things about the properties of the molecule and so on. The molar mass, that is quite often easily available for a molecule, and then the pore diameter, that is something that we need to know. And in fact, in cases like reaction engineering and so on, you do have ways to estimate the pore radius. So if you look at the BET experiments, BET, Brunauer, Emmett, and Teller, there are some well-established methods for estimating, even for very tiny particles. You can estimate the size of the pores and so on. And it's based on some very interesting experiments where you actually absorb nitrogen. So you increase the pressure, and you start condensing nitrogen in the particle, and then you controlled release the nitrogen, and the release rate that you measure can be interpreted in terms of that. So the BET experiments can be used to estimate the pore size and so on. So we won't really do that in this course, but it's just so you know that there are ways for us to estimate this. Okay, so that's if you have pure gas on gas or molecule on molecule interaction in the gas phase. And then this is if you only have molecule on wall interaction. And then, of course, we want to combine the two. So anyway, you can read exactly how the correlations can be used here. But if you want to combine the two, then what we call the effective diffusivity of A through the pore is, of course, going to be some combination of these two. So there are situations where, of course, the pore is wide enough that you don't really worry about the Knudsen diffusion. So if the width of the pore is great enough, then the frequency of collision with the wall is small, and then we can say it's purely molecule diffusivity. But when the pore volume becomes smaller and smaller, then you start to get Knudsen diffusivity, and then you have to account for both. So there are you do have to figure out, first of all, do I need to bother about Knudsen diffusion? And you can use the Knudsen number to work that out. So you estimate the Knudsen number as the ratio of the mean free path. And if you read earlier, you'll see we have ways of estimating the so-called mean free path of the molecules. And then the diameter of the pore, as we said, we can get from a BET experiment. So you can estimate a value for Knudsen. And then for Knudsen values much more than 1, we can say, well, that means my molecules are quite free to move around, and I'm not going to bother with estimating Knudsen. But if it's less than or equal to 1, then we have to estimate the Knudsen number, the Knudsen diffusivity, and then we can translate that into our effective diffusivity.
I'm having bubble gum.
So in the case of finding the effective diffusivity or the overall diffusivity of A in this mixture, which includes component B and the pores, we have to estimate this number, this alpha. So alpha is defined in this way. It's 1 plus the ratio of the molar flux of B to the molar flux of A. And if we think about the equimolar counter diffusion case, right, that means that we have equal number of moles of A and B, but they are diffusing in opposite directions. Right, so the molar flux of A is minus the molar flux of B. So if we happen to know that that's the situation, and I'll show just now when we might know that. So if we know that's the situation, then we can clearly estimate here this is minus 1, right? And then minus 1 plus 1 is 0. So alpha is 0 in this case. So in this case, we can see that it simplifies the expression. It simplifies quite nicely to that. But otherwise, we would just apply these molar fluxes, and so we need to estimate these values somehow. Or it might be that in the mass balance that we are developing, we include these as variables, and so it will appear here. And so in our diffusivity term, we will have these extra unknowns as well. So anyway, we can use this expression to estimate the effective diffusivity of component A. And then, as we promised, let's talk about when we might have equimolar counter diffusion. So let's imagine that we have a reaction surface here. So we have, so this is talking about, for example, our particles. Excuse me. So let's say we are talking about in the pores here. We have a catalyst center, and so our component A arrives on the center. It reacts, and then component B forms and moves off. Right. So our reaction is basically this one. Our reaction is A goes to B. So we have component A arriving in here. It reacts and forms component B, which then goes off here. So it's an equimolar reaction. So we can see clearly the rate at which all A is coming in here must equal the rate at which all B is leaving that surface. So that's one simple example of a case where we might be able to say it's equimolar counter diffusion. And in fact, generally, if you had some, let's say this was 2B, then it's no longer equimolar counter diffusion, but at least here we can say Na equals, well, 2Na equals Nb minus Nb. So for every 2 of A coming in, 1 of B is going off. And so in this case, we can also estimate this ratio as a number. So sometimes this ratio is related nicely to the stoichiometric coefficients. Okay, so that's how we can work with Knudsen diffusivity. We estimate the molecule-to-molecule diffusivity, and then we estimate the pore diffusivity, and then we combine the two. We have this nice relationship which helps us relate the two. So alpha is estimated in this way, and then this is, of course, the mole fraction. Now, another complication may arise, which is that our pores are not nice and straight. So if we had particles like this where the pores all looked like this, and in fact they were straight through pores, then the Knudsen diffusivity that's described applies. So you can say it applies to this specific case. But quite often it's not like that, right? You can imagine if we are trying to increase the surface area in the particle by applying stress and inducing cracks, and maybe it's through applying high temperatures and basically sintering and all kinds of crazy things going on in the particle, then our cracks are highly irregular things. And so the length of our pore is not so easy to estimate. Right, the length might be much greater than, for example, the diameter of the particle. The length may be many, many times the diameter of the particle. And in fact, it's for reasons like this that you can get some crazy values for the surface area inside particles. I've seen numbers on the order of 500 square meters per gram of particles. Right? Just think about that number, 500 square meters per gram, right? Think about 1 square meter, right? Maybe the area that you are occupying, if you project it to the floor, is about 1 square meter. Now we are talking about 500 square meters, and we are saying that that can fit inside 1 gram of particles, right? 1 gram that you can easily hold in the palm of your hand. You are fitting 500 square meters. And these are real numbers. In fact, this is not the largest value that I've seen. I've seen numbers like 2,000 square meters per gram. And that's because we can crack the particle as much as we like. We can form so much surface area that that it starts to pose real difficulty in our attempt to estimate how much Knudsen diffusion we have. Maybe just to give a clue for how we can achieve such high areas, think about a single particle, and now imagine taking a cut through that particle. Now immediately you've formed, so if that particle has a diameter of d, then just by making a single cut here, you've created a pi over 4d squared, right, area, and in fact 2, because you've got 2 sides to that. And then you can go ahead and make as many of these cuts as you like. So when you start to make these cuts with molecular type of width between them, you can start to see how you can start creating incredibly high areas here, numbers as crazy as this. So anyway, and that's tremendously helpful. Then that does things like it helps us expose a great deal more of our active catalytic sites and so on. But anyway, that makes it even more difficult for us to estimate Knudsen diffusivity if the theory is assuming straight lines passing through here. And what we do in chemical engineering, number one, we define the porosity, so the volume in all the pores divided by the total porous volume. So that's number one, an indication of what fraction of that particle is like a pore. And number two, we have this kind of joke word. This is the so-called tortuosity. So how tortuous is your path? So the tortuosity, if you have a particle here and you have a path through that molecule like this, then you can define two distances. You can define the straight line distance between 2 points across that particle. So that's one distance. And then you can also define the distance along the pore on average. So that's an indication of, or that is the definition of tortuosity. So tortuosity is the ratio of the distance along the pore, so the pore distance divided by the straight line distance. Right, so that you can see is giving us a good indication of how to correct Knudsen diffusion. So if Knudsen diffusion is assumed along a straight line, then we can just correct it by this tortuosity here. So that's pretty much what we do, and of course it has an inverse relationship. So the more tortuosity you have, the more Knudsen resistance, if you like, you have, and so the less your overall diffusivity. So so anyway, this relationship is known to hold. So you've estimated your effective diffusivity, but it's based on straight lines, and then you can correct it using porosity and tortuosity, and now you've got the actual effective diffusivity even in the face of tiny pores. Okay, so that's how we deal with diffusivity in pores. Note that this applies more to gases. I think there's a comment on this somewhere. So your liquids, if your liquids fill a pore, then the collision with the wall doesn't happen as much. So you can easily imagine if you have a liquid here, then you've got your tighter packing, and I mean in terms of molecules, you'll have a much more tightly packed molecular space, and so your collisions will be mainly a molecule to molecule. But for gases with the large intermolecular distances, the collision with the wall is a significant contributor to the overall collisions. So it's more in the case of gases that we are worried about Knudsen diffusion. Okay, so you can work through some of the nice examples given there. There's also solid mass diffusivity, so diffusion of atoms in solids, and so the vacancy in a solid, those are also interesting aspects of diffusivity, but we won't be covering that so much in the course. Okay, so that was in a sense a missing piece for us, right? Convection was easy. Diffusion is well defined, but there's this missing proportionality constant, and now we have available all these methods for getting good estimates for it. So this has set us up nicely now to be able to undertake our next topic, which is the development of our differential equations for mass transfer.